Okay, so log and exponential functions, these are inverse functions of each other. So you can see that the exponential function has a asymptote, horizontal asymptote at 0. So the log function has a vertical asymptote at 0, and they're just mirror images of each other. So when we talk about log properties, one of the main properties that we're going to use is change of base. Okay, so this is our change of base formula. We can change this base 4 into any base we want. Okay, so we can just say base A. However, we want to use the natural log in calculus. It just works perfectly for all things. Okay, any other base other than base E is awkward. So we want to use base E. So for the most part, we're going to change this to base E. So if I want to change this to base E, I end up with log, I'm just going to change colors here. We're going to end up with the natural log of x over the natural log of the base. In this case, it's base 4. Okay, so we want to change everything to the natural logarithm, which we just call the log or ln. So these ones we can just express with base E. Okay, and our calculator has base E, so we can just punch these into our calculators afterwards. But this becomes log 6 over log 3. Here we end up with just log 4e squared over log 3. Now, when we have the base and the argument match bases, we should probably evaluate this. So this should work out to be log 4 plus log of e squared is 2, and that's all over the natural log of 3. So here we're going to change this to base E. So log 3x divided by log 2. Here again we have, well, in this case we have base x, exponent x. Are those related, and can we simplify them? Well, let's see. Let's change this into log base e. So we get 10 to the power, 10e to the power 3x. Okay, and then we get log x. Okay, so there's a base e involved here, so we should simplify this into log 10 plus log e to the 3x, which just becomes 3x, over log x. Okay, and notice that the base x and exponent x here have nothing to do with each other, so we cannot do anything algebraically with those two terms. Okay, so we want to change everything to natural log, because that is when we start doing the calculus will work much better with the natural log or base e log. So there's some basic identities that we should know for logs, and we should try to use these identities when we see them. So basically the first two, the top ones at the top, are showing that the log and the exponent undo each other and they get the x. Same thing here, where the exponent and the log, they're going to undo each other and give us x. Okay. The log base a of a, so anytime we have the base a of a, it's going to be equal to 1 because a to the 1 equals the argument a. Here, the log of 1 always equals 0 because the exponent that gives us this argument 1, the exponent on the base always has to be 0. Okay, so that's an identity we should always try to use. This last one here, you may not have seen this one before, but we can reduce the powers on the base and arguments proportionally. And the reason why is this, and I'll just show you a quick proof of this. So if I have log a to the power m and I have x to the power m. Let's say that's equal to y. Okay, so that means that if I put this in exponent form, it's going to look like this. A to the power m y equals x to the power m. So you can see that when we actually put that in exponential form, we can see that this m and this m, they're both exponents on both sides. So we can reduce that power. We can root m, and we can root m on both sides to actually get rid of that m. Okay, because these powers here, the power on the base here and the power on the argument here, they're actually related to each other through this equation like this. And they are connected essentially, and we can undo them together. And so we end up with a to the power y equals just x. And so we can get rid of that m, or introduce m. In fact, we can go the other way. And then we can rewrite this as log base a of argument x equals y. Okay, so then we can say that these are equivalent expressions to each other. Okay, so that's a useful property if you ever run into it. Now you don't need any of these properties because we can do logs multiple different ways as long as you're not making up some new rule. And that's the big thing about logs. Don't make up some new rules that don't exist. Okay, so let's re-express this as a single log. So we're gonna put this into the exponent into the log. So positive logs are in the numerator, negative logs are in the denominator. Okay, because negative log means it's negative power, which means to divide. Now this first one, it doesn't ask us to solve it, but we can actually solve this because it is an equation. So I'm going to combine these. I'm going to put the logs on, in fact, I'm going to put the logs all on one side, and then we'll solve it that way. Okay, because there's two ways to get rid of logs. We can get rid of logs by making log equal log and dropping logs. Okay, that would probably be what we would maybe choose here, but it does ask to express as a single log. So I'm going to put all into one log, and we can get rid of logs as another way by using definition of log. So this is going to be positive logs are in the numerator. All the negative logs are in the denominator. It's a little bit nicer. X squared minus 1 and divide by 4, because that's a negative log, and that's equal to 0. Okay, and then we can get rid of this log by just writing it as a to the power 0 equals x plus 3 all squared over 4x squared minus 1. Again, this is all it does is ask you to put it into a single log, which is what we've done here. But since this is an equation, we can solve it. Let's go ahead and solve this. Okay, so we end up with, that's going to be equal to 1. So we end up with 4x squared minus 4. That's equal to x squared plus 6x plus 9. I think we might have to use a quadratic formula for this one. So we end up with 3x squared minus 6x, and that's going to be minus 13 equals 0. And then we can put that into the quadratic formula. Okay, so we might as well finish this off. X is equal to 6 plus minus square root of 6 squared minus 4 times a times c. That's all going to be divided by 2a, which is 6. Okay, so when I write this out, so that's going to be 12 times 13, which is 156, I think it is. Okay, so then it's going to be 36 minus negative 156, so that's going to be 192 all over 6. Okay, so there's our value of x, because since there's an equation, we went ahead and solved that. Okay, for this one here, we can just solve this one as well. Let's use our log properties. Here we can rewrite this as a to the power 2 log base a of x. In fact, I'm going to skip a step here, and I'm going to just put that as x squared, because that 2 can apply to the exponent. Okay, and then we end up with 3x minus 2. So this is an identity. That just becomes x squared equals 3x minus 2. Make it equal to 0 and solve that quadratic. Okay, so when we factor this, we end up with x minus 2 times x minus 1 equals 0, and then x equals 2, x equals 1. And we just have to make sure that when we solve these log equations, that we check for extraneous solutions. Okay, so can we put 2 back into this equation? Can we put 1 back into this equation? Yeah, both are okay. Therefore, these are good solutions. I'm just going to make a note here. Always check for extraneous solutions. Okay, so always check for extraneous solutions. Okay.